So today we are working on balancing isotope reactions. And as you can see here, I have some example problems. So by the end of this video, you're going to be able to do all of this, and this is going to make sense to you. Right now it probably looks like gibberish, but by the end of the video, you should know what all of this means. So first we have to know what an isotope actually is in order to balance an isotope reaction. So an isotope is just a different version of the element. And by element, I mean, anything on the periodic table, neon or oxygen or carbon or anything like that. How is it different? It's different because of the number of neutrons is going to be different from the number of neutrons in the regular normal element, how it normally appears on the periodic table. Now, each element is identified by its atomic number. So that means if we have a C for carbon and above it on the periodic table, it's got the little number 6 there, and down here on the bottom it has usually a 12 or 12.01, something like this. This is going to be its atomic number, and every atomic number for every element is different. So if it has the atomic number of 6, then it's carbon. It's going to be C carbon. It doesn't matter about anything else. If for some reason there's a change in mass, this is the atomic mass number. And if for some reason it's not 12.01, if for some reason it changed, any changes, if you go back and you look at the atomic number, if the atomic number is still saying 6, then we are dealing with carbon. If carbon has 2 plus at the end of it, we're still, but that atomic number is still 6, we're still dealing with carbon. And you'll see why I'm making such a big deal about this here in a second. Here is the periodic table, and here's what I was talking about. Here's carbon up here, and see it says C, and then there's a 6 above it and 12.01 below it. On the periodic table, when you're reading on the periodic table, this top number up here is the atomic number, and as you can see, everything is organized by the atomic number. Hydrogen's 1, helium's 2, lithium's 3, beryllium's 4, boron is 5, carbon 6, nitrogen 7, 8, 9, 10, and so on, all the way down to, well, 118. So as you can see, the atomic number is what organizes all the elements on this periodic table in numerical order. The bottom number is the atomic mass. So that's like, mass is similar to the weight. We would call it weight on Earth, but if you're on the moon and the gravity is different on the moon, you would weigh less, but the mass stays constant. So there's an actual difference between mass and weight, but while you're on planet Earth, mass is the same as weight. So you can say atomic weight or atomic mass. This is the atomic mass unit, 12.01 atomic mass units. So I'm telling you all of this to show you this, to concentrate on the atomic number, number 6 for carbon up here. So once again, here's the carbon element with its atomic number 6 right on top here. Now the atomic number actually stands for something. It's not just the number of squares where the element is on the periodic table. The atomic number actually stands for the number of protons in the atom. Now, in case I need to remind you, the protons coexist with the neutrons in the nucleus. Now, the protons and neutrons are very similar particles. They're the same size and the same weight, or the same mass. They're different in the sense that a proton has a positive charge, while a neutron is neutral. That's where they get the word neutron from. It's neutral. So it has no charge, zero charge, no charge. But they weigh the same. The only other element in an atom is outside of the nucleus, and that's the electron. So electron is obviously a negative charge. And the thing about electrons is that they are so tiny, their weight or their mass is negligible. So we don't count their weight. So I'm going to put 0 here. Now, the thing important about the number of protons and why the atomic number is named for the number of protons in an atom, because in a normal atom, the atomic number is always the number of protons, no matter what. So the atomic number is the number of protons. So there's 6 protons, so this is a carbon. But the number of protons, normally, the number of protons default to equaling the number of neutrons, because the neutrons and the protons both hang out in the nucleus, and they're buddies. Because the protons are positive, so they're not annoying, they're not negative people, they're positive. So they make good roommates. So the neutrons are neutral, so they don't really stir up anything, and there's no drama with the neutrons. Neutrons don't have any drama, so they make good roommates. So the protons and the neutrons pretty much hang out together in the nucleus as roommates. And they want to make sure that they protect each other and, can both chip in on the bills, on the rent, and buy food and groceries and everything. So usually in a normal element, as presented on the periodic table, the number of protons in the nucleus is going to equal the number of neutrons. So in this case of carbon, the atomic number is 6. That means it has 6 protons. Because it has 6 protons, that means it has 6 neutrons. Also, another thing about the number of protons is that the number of protons in a normal element, as presented on the periodic table, the number of protons also equal the number of electrons. And remember, the electrons go around in those orbits outside of the nucleus. They orbit around the nucleus like planets around the sun. So, and the protons and the neutrons are both inside the nucleus, or inside the sun, you could say. But the reason why the number of protons and the number of electrons are the same is because the element on the periodic table is written as it has a 0 charge. So if protons are positive and electrons are negative, then you have to have an equal number of both protons and electrons to have a 0 charge. Because if we had one more electron than we had a proton, then it would be a 1 negative charge. If we had 1 less electron than we have protons, it would be a 1 positive charge. So, but that does not affect the atomic number being the number of protons. The protons stay the same. The number of protons stay the same. There's always 6 protons in this carbon, and 6 protons always mean the atomic number of 6, and the atomic number of 6 always means carbon. But the electrons will change. You can gain or lose electrons, and that's going to change the charge of something, and so then it could be like a -1 or it could be a +1. But as it's presented on the periodic table, those elements have a 0 charge, a net 0 charge. If the atom loses an electron or gains an electron, so it has a -1 charge or a +1 charge, or maybe even it gained 2 electrons, it bumped into some other atom and took 2 of its electrons, then it would have a 2 negative charge. Or what if the atom lost 2 electrons? It would have a 2 positive charge. All of these situations here where there's a different number of electrons than there are protons, so the element ends up having a charge, these are called ions. So you can have a carbon ion let's say the carbon ion has a 4 negative charge. So that would be a carbon ion. And it's not going to change that 6, that atomic number up there. It's still going to be the atomic number of 6. We're just going to put a 4 and a negative sign right next to it to indicate that this is a negative 4 charged carbon atom, which is called an ion. So this is a carbon ion. Now, going back to the neutrons up here, if the number of protons in the nucleus of an atom is the same as the number of neutrons, usually. But when the number of neutrons changes, this is called an isotope. So, see, when the number of electrons change, it's called an ion. When the number of electrons change, and when the number of neutrons change, it's called an isotope. Let's go back to this point that I made earlier over here on the right, that protons and neutrons, the proton is a positive charge, the neutron is a neutral charge, and that's the difference between protons and neutrons. But the similarities of protons and neutrons is that they both weigh the same. So in order to get the weight or the mass of this element, you add the number of protons plus the number of neutrons. So the number of protons plus the number of neutrons is the mass, the atomic mass. Now, why is that important? Well, because just like when the electrons, we lose or gain an electron in an ion, and so we indicate that by putting like a little 4 negative on the end of the element abbreviation, so we know that that's an ionic charge. The way you write an isotope is you calculate what the new mass is now that the neutrons have changed. And I'll show you an example of that. Now, for instance, and I wrote this fact down here on the bottom just as a reminder, the number of protons plus the number of neutrons equal that atom's atomic mass or atomic weight. So in carbon, there are normally 6 protons in carbon. So let's put that down here. So 6 protons in carbon, and so that means there are usually 6 neutrons in carbon. So the standard carbon atom as presented on the periodic table, just normal, is 12 atomic mass units. And as you can see down here, this is approximately 12. There's a reason why you don't look at the atomic mass number or the atomic weight on the bottom of the periodic table when you're calculating isotopes. And I won't get into it, but there's a reason why because this is actually the average of all the isotopes together. But for your understanding, the 6 protons means there's 6 neutrons, and they both weigh the same, so they both weigh about 1 unit, 1 mass unit, and so that makes 6 plus 6 makes 12 atomic mass units is the weight of a carbon atom. However, what if this carbon atom for some reason loses a neutron? So now we don't have 6 neutrons in this carbon atom. For some reason we have 5 neutrons in this carbon atom. So that would make this 12 atomic mass units wrong. This would be 11 atomic mass units. And what do we call it when there is a change in the number of neutrons to an element, we call that an isotope. So the isotope, the weight for the isotope of the carbon with 5 neutrons is 11 atomic mass units. So therefore, when we're talking about a carbon atom that has lost a neutron and become an isotope, and so therefore it has 11 atomic mass units, we refer to that as carbon 11. So see that number, we refer to that isotope with that number attached to it, and that number is what the atomic mass units are, which is the total number of protons and neutrons in that isotope, in this case 11. And we can do a different one for carbon. So carbon has an atomic mass of about 12, so that's 6 protons, and the 6 protons don't change if it's carbon. If the 6 protons were to change, if that number were to change, then we wouldn't be talking about carbon anymore. So, but the 6 protons plus the 6 neutrons in a standard carbon atom is 12, so that's the atomic weight. And we just did, if we lost a neutron, that would be called carbon 11. That's an isotope. So what if we gained 2 neutrons? So that would be 6 protons. That would be an isotope of carbon, since it has a different number of neutrons. That would be a total of 8 neutrons. And if you add those together, 6 protons plus 8 neutrons are 14. So 14 would be the atomic weight number. And we would call this isotope C14, or carbon 14. And again, that would be an isotope, because the isotope is when the amount of neutrons are changed within an atom of the element. Now, one more thing about writing isotopes. First we did the carbon with 6 protons and only 5 neutrons, so that's an isotope because there's different number of neutrons than there are protons. So we would write that C11, and the 11 is the 6 plus 5. So that's the atomic weight, so carbon 11. But when you write it down, you'll also see it written down like this. You see the big C written down like, it looks like it's from the periodic table, but it's not, because instead of on top, like normally on the periodic table, you'd have the 6 on top and the 12 on the bottom, right? But when you write an isotope, you write the element's symbol, just like on the periodic table, but you take this atomic mass, the atomic mass number, and you put it on the top left corner of the element. So you would put 11 up here. And some people also take the atomic number and put it down here. So you would have C11 on the top and 6, and these are in the corners. They're not on top and on bottom like in the periodic table, like over here. They're off to the side. So sometimes you'd see 11 and then the 6 on the bottom of the C. Sometimes people would just write it C11 like that if they're being lazy, and sometimes people will write it like that. It all means the same thing. It's a carbon 11, and that's an isotope. And it's an isotope because why? Because there's a different number of neutrons than protons. So we're going to stick with writing the isotopes like this, because that's how you're going to be able to solve these equations at the end of this video. So we're going to have the mass number up in the left-hand corner, and I think it looks like a Scrabble tile or something. And we're going to have the atomic number, just for a reminder, and that's the number of protons in the bottom left-hand corner. So now that we've gone over that part, the part about isotopes, how they're calculated, how they're written, and what they are exactly. You need to know one more set of things. You need to know about nuclear chemistry, just a little bit about nuclear chemistry and decay. So first we have alpha decay, and the alpha symbol looks like this. It's kind of like a little cursive A or like a really flat fish. So alpha decay is going to emit, and by emit, I just mean give off. So alpha decay is going to emit 2 neutrons and 2 protons. So we're going to write it like this. The alpha decay, we're going to put a big E for just a generic element, just any element. What it's giving off 2 neutrons plus 2 protons. Now remember, in isotopes, you add the neutrons and the protons together to get the atomic mass, and you write it in the upper left-hand corner next to the element. So 2 neutrons plus 2 protons is 4. So 4 is the atomic mass unit, so we're going to write a 4 in the upper left-hand corner next to this element, notated by the capital letter E. And then on the bottom left-hand corner, we're going to write 2 for the 2 protons, because remember, in the periodic table, the atomic number is the same thing as the number of protons, and that's written in the bottom left-hand corner when you're doing it in isotope form. So this is what it looks like: 4 on the top and 2 on the bottom, and just a big capital E to stand for any element that we're talking about. Now, what happens if you look on the periodic table? 2 protons is going to be this 2 up here. That's its atomic number, which is equal to the number of protons. And 4 down here on the bottom is the atomic mass. The atomic mass number, which is equal to the number of protons, I'll just put pro, plus the number of neutrons, I'll just put nu. So that's going to equal 4, and that's down here. Well, what is this element that has 2 protons and its atomic mass is 4? Well, that's helium. So going back to our other page, this electron, this generic E, with an atomic mass number of 4, and the atomic number, or the number of protons, is 2, well, that's the same thing as helium. So this alpha decay is the same thing as emitting a helium atom without its electrons. So that would be 4, and that would be 4 is the mass and 2 is the number of protons. And this is called alpha decay. Now there are 3 more types of decay that you need to know, and I'm going to present these next 2 side by side with each other because they're really similar. So beta decay is one of them. And beta looks like this. It looks like a misshapen B, or like a fancy B. And the other one is positron emission. And positron emission doesn't have a little fancy symbol to go with it. Now, beta decay is an electron emission. It's the same thing as an electron emission. And remember, emission just means to emit, to give off. So this is giving off an electron. An electron emission is beta decay. There's beta. Now it only gives off an electron. So it doesn't give off any mass, because remember, electrons don't weigh anything. Or I mean, they do technically, but it's so minimal. It never factors into any of the math and the calculating you have to do with chemistry. So we just pretty much say that electrons have a zero mass. So the atomic weight of an electron being given off, the atomic weight would go up in the upper left-hand corner again. So like here's the square, like on the kind of like I always think of it as a Scrabble piece. So up here on the upper left-hand corner would just be a 0. And the bottom part, the bottom part would usually be the atomic number of an element. But we're not talking about an element, we're talking about an electron, any electron. So an electron has a charge of -1. So we just put down the charge of -1, and instead of that capital E I was using to represent any element on the periodic table, we use a lowercase e to represent the electron. So that's how you're going to write a beta decay, is the 0, the -1, and the e, the lowercase e, to represent that it's an electron. So what happens is that the neutron emits the electron. And I know that sounds weird because, well, you have this, you could say, well, Suzanne, you have in an atom, you have the nucleus where the protons and neutrons live, but then you have the shells or the orbitals around it, and that's where the electrons are, is around here. So how would a neutron give away an electron? Well, that actually is what happens. The neutron, since the neutron, which lives in the nucleus, since the neutron normally has a 0 charge to it, it gives off a negative charge. It gives off the -1 charge of an electron, so the neutron itself becomes positive. Now, what is a positive neutron? Because by definition, a neutron is neutral. A neutron has no charge. So what happens when a neutron gives off a negative charge and it becomes positive? Well, that turns the neutron into a proton. So what you're actually doing is, in beta decay, the neutron is giving off a negative charge equal to that of 1 electron, and the neutron turns into a proton. So you are adding a proton to this atomic structure. Now, I know you're probably saying, but Suzanne, you said the protons numbers never change in the element. A carbon is the atomic number 6, and that means 6 protons. And no matter what, if it has 6 protons, that means it's carbon. Now I'm saying that this neutron is turning into a proton and adding a proton to the atom. How can that be? Well, because if, say, you have this 6 protons for the carbon, and you add a proton to it, that's going to end up being 7 protons. So the atomic number would be 7 all of a sudden instead of 6. Well, let's look at the periodic table and let's look at this carbon. Here's the carbon and the atomic number is 6, but we added 1 proton to it, so now the atomic number is 7. Well, what is atomic number 7? Atomic number 7 is nitrogen. So by beta decay, we have turned a carbon atom into a nitrogen atom. So because the nitrogen is the one that has 7 protons, its atomic number is 7. So this beta decay actually changes the carbon into nitrogen. Now, positron emission, on the other hand, and positron doesn't have any fancy little b or a for alpha and beta decay. We just call it positron emission. In positron emission, the proton gives up its charge, because remember, protons are, each proton has a positive 1 charge to it. Proton equals a positive 1 charge. But what happens in positron emission, the proton gives up its positive 1 charge. So, bye-bye, positive 1 charge. The proton gives that away. So what do you think happens in positron emission to the proton if the proton gives up its +1 charge? Because by definition, a proton has to be a +1 charge. But that would mean if the proton gives up its +1 charge, now it has a 0 charge. But what other item in the atom has a 0 charge that would fit that definition? Well, that would be the neutron, because neutrons have no charge to them. So positron emission is literally the proton giving up its positive charge to become a neutron. So that lessens the proton amount in the element's atom, which would change the atomic number, which would again change the actual element. So if we go back to our periodic table, so here's 6C right here. So it has 6 protons right now, and it's carbon. But if it got rid of its positive charge, then it would only be 5 protons, because that 6th proton turned into a neutron. Well, 5 protons is boron right here. So positron emission will literally change the element from one element to an element before it with a lower atomic number. And that is written like this. You got a 0 up here because the the proton is just giving away a charge which has no weight to it. So we're not changing the weight. So the weight, the atomic mass, the weight stays 0. So we put the 0 up here, and we just put a positive 1 down here. Note the difference between, in the beta decay, we have a negative 1 down there. Positron emission, we have a positive 1 down here. And we still use the little e for an electron because we're still talking about charges. So as you can see, this is why I wanted to put these together for you, because they're the opposites of each other and they're written almost exactly the same. Beta decay has a negative 1 at the bottom left because it's giving away an electron and a negative charge. So that turns the neutron into a proton. And positron emission has a positive 1 down at the bottom because the proton is giving away its positive charge. So that means the proton turns itself into the neutron. So see, they're exact opposites of each other. And that also explains why they're written so similarly. Now the last type of decay that I need to talk about, and then we'll get to the solving those practice problems, is gamma decay. And gamma is this little weird looking V thing. And gamma decay is a bit different because it doesn't change the protons or the neutrons. So it does not change protons or neutrons. So what does it do then? It excites the atom. I don't know, maybe it bought it a winning lottery ticket or something, but it got the atom all excited. And the protons and neutrons in the nucleus, and you should know this by now that they're in the nucleus, they get rearranged. And they are grouped together tighter. And when they get so close together, it builds up some energy. And what happens as a result it shoots out a gamma ray. And this can be very dangerous. Like, I think somebody said, like, an alpha decay, if an alpha decay is emitted, it'll be stopped by your clothing. If a beta decay is emitted, it'll be stopped by your skin. But a gamma ray will go straight through you. So there's this atom, here's the atom, and here's the nucleus. I'll make the nucleus bigger so we can see. And in the nucleus, it rearranges the protons, and it rearranges the neutrons. So they're really, really tightly packed. And what happens when they're tightly packed together, it shoots out a gamma ray. So how we do that is how we write this. Like if we go back to using E as just a generic element, it doesn't change the weight of anything because it's not shooting out a proton or a neutron. There's still the same amount of protons and the same amount of neutrons in there. So the weight does not change. So we just put a little 0 up there. And it doesn't shoot out, since it doesn't shoot out protons, it's not changing the atomic number. So we can just put a little 0 down there. But that's just for me to explain it to you. Really, they just use that funky looking V instead. They don't really use that kind of notation. They just use this funky looking V and expect you to know that it made this, that something made the atom, put the atom in an excited state, which rearranged the protons and the neutrons and got them all close, huddled up together in the nucleus. And their closeness, being huddled up together, gave off energy enough to shoot out a gamma ray out of the atom. So if you want to write this as an example, let's look at our periodic table again. So let's look at iodine here, for example, on the periodic table. Now iodine is atomic number 53. So here's iodine, big ol' I. And iodine is atomic number 53, which means there are 53 protons in the iodine. And let's just say that this is, since we're writing it in isotope form, this is isotope form, putting the 53 on the bottom instead of the top. This is an isotope where the atomic weight actually is 123. And that's an actual isotope of iodine. So we're going to write this we're going to have this isotope 123, iodine 123. Remember, we could do it that way too. And that means an isotope of iodine that weighs 123. So say we have 123, or iodine 123, and it has a gamma decay to it. So I'm just going to put plus that little V, that little crazy little V. Well, the V, remember, the V weighs nothing and gets rid of no protons. So there's nothing that happens, but but in the gamma decay, the iodine, this iodine isotope, gets really excited in order to shoot out this gamma ray. So we denote the iodine isotope getting really excited to shoot out a gamma ray by putting a little asterisk next to the I. So the only thing that happens is that an excited isotope of iodine shoots out a gamma ray and leaving with a not excited isotope of iodine with all the same numbers to it. See, nothing changed. Still 123 on top, still 53 on the bottom. It's just not excited anymore, so we don't have that asterisk here where we did at the beginning. So an excited iodine isotope will shoot out a gamma ray and leave us with a not excited isotope of iodine. It'll be the same numbers and everything. So the gamma ray actually is really easy to calculate because you're not calculating anything. You're not adding anything, you're not subtracting anything. It's going to be the exact same numbers either way.